In this paper, we show a surprising fact that running the policy itself is not the optimal way to evaluate it. Therefore, we propose an optimal behavior policy for policy evaluation. We show that our method saves up to 80% of online data in different environments. Reinforcement learning requires massive online interactions, which can be very slow. For example, in an industrial cooling system for Google, each interaction with the environment would cost 5 minutes. In order to train a deep RL algorithm with 5 million steps, the total running time will be more than 3,000 days. A common approach to address this problem is to design a simulator and reduce the step time from 5 minutes to 10 seconds. However, in order to train a deep RL algorithm, we still need more than 100 days to complete the training. Another approach is to use offline RL, where offline RL agents are only trained on offline data. However, there is a common problem for offline RL algorithm, which is how to tune the hyperparameters. There are three approaches in offline RL community. The first is to ask a graduate student and do a stochastic graduate descent. The second is to copy the hyperparameter from another paper. And the third one is to use online data to train the offline RL algorithm, which is somewhat cheating because we still need online data to tune the hyperparameter for our purely offline RL algorithms. Moreover, to evaluate the trained algorithms, only use offline data introduce uncontrolled bias. Thus, a policy might perform really well on offline data, but it's actually very bad in the real data. Therefore, we can say that both online RL and offline RL use online policy evaluation to evaluate their algorithms. Thus, to address such need, we design an optimal behavior policy for policy evaluation. We also introduce an offline learnable behavior policy, which is proved to reduce variance. We can say in our main theorem, we proved that the variance of off-policy estimator with our designed behavior policy mu height is always guaranteed to be smaller than the variance of the on-policy estimator. We also show that empirically our method saves up to 80% of the online data. That is, to achieve the error that online MC achieve with 300 steps, our algorithm only needs 60 steps to achieve it. That means we can save 80% of the online data. We also compare our algorithm with other algorithms. That is, we achieve superior performance compared with online Monte Carlo, behavior policy search BPS, and robust on-policy sampling ROS in different environments. From the table, we can say in different module robotic control tasks, our algorithm improved the saved samples by at least 200%. Also, in large grid words, for example, grid word with size 1,000 and 27,000, our algorithm, the blue line, consistently dominates other methods by a large margin. In the future, we plan to extend our method to policy improvement. That is, we plan to save the data needed to train our algorithms such as DQN and PPO.